everyone. So for learning task 3, we will be solving some problems from problem set 3 of Analytical Chemistry Lecture 2. Question 2621 reads, if Vs and Vm for the column in problem 26-18 are 19.6 and 62.6 ml respectively, and a non-retained air peak appears after 1.9 minutes, calculate A. the retention factor for each compound, B. the distribution constant for each compound, and C. the selectivity factor for methylcyclohexane and methylcyclohexene. So for question 2621, the given are the Vs and the Vm values at 19.6 and 62.6 ml. And from problem 26-18, this is the data. So you have your air, methylcyclohexane, methylcyclohexene, and toluene, and the retention times and the width of their peaks. Now for the solution, the retention factor is defined as K is equal to Tr minus Tm over Tm, where Tr is the retention time of the component and Tm is the retention time of the carrier gas, which in this case is air. So for methylcyclohexane is computed as such, with the Tr of 10 and the Tm of air at 1.9, that gives us a value of 4.2632. For methylcyclohexene, doing the same, but for K of 10.9, it gives us 4.7368. And for toluene, for a TR value of 13.4, it gives us a K value of 6.0526. Now the distribution coefficients for each component are defined by this formula. K is equal to K multiplied by Vm over Vs. For methylcyclohexane, we substitute the K value obtained from letter A, and that gives us a capital K value, which is the distribution coefficient of 13.616. Doing the same for methylcyclohexene gives us 15.1289, and for toluene, that gives us 19.3314. Lastly, for letter C, the selectivity factors for methylcyclohexene and toluene are given by this formula, which takes the ratios of the retention times of the component which has a greater retention time over the component which has a less component time, subtracted to the retention time of the carrier gas. It's given by this formula here. So for methylcyclohexene, we take the retention time of methylcyclohexene as 10.9 and methylcyclohexane as 10, and we substitute that to this formula here, and that gives us a selectivity factor of 1.1111. Doing the same for toluene, given that the retention time for toluene is 13.4 and the retention time of methylcyclohexene is 10.9, that gives us a value of 1.2778. What these values pertain to is that separation is possible because the selectivity factors are greater than unity. Now for question 2821, an HPLC method was developed for the separation and determination of ibuprofen in rat plasma samples as part of a study of the time course of the drug in laboratory animals. Several standards were chromatographed and the following results were obtained. You have here the ibuprofen concentration in micrograms per milliliter and the relative peak area as these concentrations were passed through an HPLC. Next, a 10 mg per kilogram sample of ibuprofen was administered orally to a laboratory rat. Blood samples are drawn at various times after administration of the drug and subjected to HPLC analysis. The following results were obtained. You have here your time, in hours and the peak area. Now we are asked to find the concentration of ibuprofen in the blood plasma for each of the times given above and plot the concentration versus time. On a percentage basis, during what half-hour period, such as first, second, or third, is the most of the ibuprofen lost? And the problem, this here is a diagram. So you first subject your ibuprofen standards via an HPLC and you get the relative peak area. These are for the standards. Now for the samples of 10 milligram per kilogram ibuprofen, it was administered to a lab rat and blood samples were taken at different times in a per hour basis. And it was subject to an HPLC and the peak area was determined. So first, the concentration profile can be obtained by plotting the relative peak area, which is the y-axis, versus the concentration of ibuprofen in the x-axis in micrograms per milliliter of the ibuprofen standards. So basically, we'll be taking the standards first and creating a linear equation so that we may determine the concentration of the samples by using the equation obtained from the standards. So plotting, it gives us this graph here, and the equation of the line is 6.2669x plus 3.2695. This is the equation of the line that we will be using as a reference to determine the concentration of the ibuprofen at the blood samples taken at different hours. Now, again, we obtain the equation of the line, and using the data obtained for the last rats are administered with ibuprofen, the concentration of ibuprofen at different time intervals can be obtained. So here is a sample calculation at time is equal to 0.5 hours. The concentration for ibuprofen is given as y minus 3.2695 over 6.2669, where y is the peak area. The peak area at 0.5 hours is 91.3. So plugging that into this equation gives us a concentration of ibuprofen of 14.046684. Doing that gives us this table, where we have here the concentration of ibuprofen in micrograms per milliliter over the course of the time interval given in the problem. Now the percentage change per 0.5 hour is calculated by this equation here, where CT1 is the concentration at the preceding time interval, and CT2 is the concentration at the latter time interval, all over the concentration at the preceding time interval multiplied by 100. So here we have a sample calculation using the first two concentration values obtained from the data. Percent change is equal to 14.046884 minus 12.275676 all over 14.046884. 14.04 here is concentration at 0.5 hours. 12 here is the concentration at 1 hour. And we get the percent change as 12.6093%. Tabulating yields us this table here. The change per 0.5 hours only begins here at the 1 hour mark because there is no concentration at time is equal to 0 hours, so we cannot obtain a change per 0.5 hours between 0 and 0.5. Now, for 2 and 3, the concentrate it has an interval of 1 hour, so the appropriate calculations were done as to be consistent with the over 0.5 hour change, as also is the case with the 4 to 6 hour interval. Now from the table, you have here the time in hours and the percent change per zero point 0.5 hour. We are now tasked to find which of these gives the biggest percentage loss of ibuprofen in the blood samples of the rats. Looking at the table, the largest percentage loss occurs between 1 and 1.5 hours because the value here is at 36.52645, and that value is the largest value in all of the tabulated values given on this table. Thus, the largest percentage loss occurs between 1 and 1.5 hours. That is it for this learning task. Thank you and have a nice day.